Okay, so the thing that we were looking at yesterday is that unlike OCaml, where for simple functions at least there is a best possible type that you can give for a function. Even here in F star, there is a best possible type for a function, and such type is going to be the subtype of all of the other possible types that you can give for the function. And the example that we saw was this increment function, which the refinement here precisely captures the specification, but you can have arbitrary refinements that are sort of weaker than this refinement. Okay, so let's continue and switch to the slides. So the thing that I want to talk about next is um, so every function that we've been seeing so far is what is known as a total function. Um, the word total means totality in the mathematical sense. What does that mean? A total function is something where the function does not have side effects and it terminates on all inputs, right? So it's not, it is known to terminate on all inputs. So those functions are what we call as total functions. In Galena, when you define a function, right, using a definition or a fixed point, every function is in fact a total function. Because if Coq, the language side of Coq, which is the Galena language, if it accepts a function, if it says this type 6, it is in fact a total function. The way, if you go back earlier, right? So I mentioned this air gap between real languages which have effects on the right hand side, but with not rich logics. But then here we have really rich logics, but interactive proof assistance. The thing that F star brings to the table is that it is an effectful language, just like ML. You can have references, you can have exceptions, you can have concurrency. I mean, concurrency is not directly encoded, but you can have concurrency. You can have so many other things, right? So the way these are captured is that we have this notion of an effect that is reified, that is actually made concrete in the language. So every function that we've defined so far is called this total function. We have an effect called tot effect, right? Which is the default effect for if you declare a function type without with just say nat to nat. Implicitly, there is the assumption that the function is a total function. This is equivalent to writing the same type as val factorial. This factorial function takes a nat, right, and returns a nat, and the effect it has is a total. I mean, the function itself is a total function, right? By totality, we mean that there are no side effects and it terminates on all inputs, right? So that's the observation there. Just considering this function, right? So we gave, you can look at the factorial function here, and we have this definition here. And what would happen if we changed this type definition that we have here into int arrow tot int? Would you think the program will be accepted for this particular changed type? So the only thing that I'm changing is I'm changing the nat to int, right? Do you think this function will type check? Recall that what do we mean by total function? Total function should not have side effects, and the total function terminates on all inputs, right? The function definition is here. And the question that I'm asking is if you replace this nat with ins, would this function still type check?
So if you start with a negative, that might not work, right? Int contains negatives.
Precisely, Shashin. So because if you the contract, I mean, you sort of have to think about contracts all the time, right? The contract is that I can accept any integers here, and if you look at getting a -1 here, the condition here states that it's if it is n equals 0, then it terminates. But if n is negative, you just keep on going, right? So and the thing to remember is that just like Cox's definition of integers, we have infinite precision integers here. These are integers are not of fixed size. So the function will not terminate, right? It will go into an infinite loop. And precisely for this reason, um, if you write this function, you will get this error which says that subtyping check has failed. I expected let's come back to this one. I expected something which is going to terminate, but I got an integer. I mean, we will see what this less than thing means. But factorial minus one loops forever. That's the idea, right? The fact that I'm saying it's total, I cannot the f star type checker cannot prove it. So it will not let this function to compile. So let's actually see this in practice. So here is the factorial function again. So all I've done is I've added total here, right? But otherwise the function is the same. So this works, right? And if I change the factorial function to have, and all I'm doing is that I'm sort of defining factorial 3 where I'm just saying, consider this function to be an integer to total integer. This won't work, right? It says subtyping check has failed because it's just the fact that it cannot prove the termination. Okay, so there is something about this termination where we are saying, okay, there is this notion of a termination that the F star is actually trying to prove. We had this notion of termination in Coq as well. In Coq, of course, we can't prove termination for general case, right? If I give you a program and then ask you whether this program will terminate, that is undecidable. This is the definition of a halting problem, right? So you have to come up with some mechanism in order to uh, ensure that the functions that you write can terminate. The way Coq decides is that um, the recursive calls should be on smaller subterms, right? So that's the idea that Coq uses. Of course, there might be functions which can be rejected. You have to sort of work around it, but we have a different notion of termination here, which is sort of like building upon that. But because we have an SMT solver here, we can be a little bit more relaxed in what we allow, right? And in particular, if you look at this definition here, so I have a n here, I have n minus 1 here, right? And I have a total effect here. So F star is able to prove during type checking that this function terminates. This function, if you had just written it in a similar way in Coq, would not type check. So it knows something about the natural numbers, right? That it terminates at 0. So that's the key thing that you have to keep in mind. But let's look at what the termination checking actually means. So F star uses this idea known as semantic termination checking. We won't go too deeply into this, but the idea is this, right? So um, this less than that you see here refers to what is known as a well-founded ordering on expressions. Okay, so if I give you an expression and another expression, I can relate those two expressions by less than, and the definition of that particular relation is given here. So if the left hand side and the right hand side are natural numbers, then they are related by less than, right? And if you give negative numbers, they are unrelated. So if you have negative numbers, then this definition is not there. Similar to Coq, for inductive types, right? Inductive types are related by subterm ordering. So if I have a list which has two elements, and I have a list which has just the tail of the list, then the tail of the list is semantically smaller than the original list with the head and the same tail. Okay, that's the second one. And thirdly, we have this thing called lex tuples. This is just fancy syntax, but it's just lexicographic ordering, which is extension. So it says when you have an expression such as this one, and I have say a prime, b prime, c prime, you just look at lexicographic ordering. So you first consider a. If it is related by this relation, okay, then this whole term is related by that relation. If they are equal, then move on to the second one. Similarly, you keep on going. It's just a matter of saying how do you chain this thing together, right? So you keep applying it, and this is like the inductive case, right? These only these two are the base cases for this, and that's the entire rule for well-founded ordering, right? So this ordering constraints, right? because we have a less than relation on natural numbers, these constraints are actually discharged by the SMT solver. So we don't have to do too much work in order to describe this. If you sort of think about this, we didn't explicitly have to do this so far, right? We've only seen small functions. We haven't we didn't need to do anything special for termination checking. It happens very naturally because the default metrics that are chosen for this are quite sensible. So here is an example just to show if you wanted to do something more fancy, right? In order to show that a particular function terminates, what you can do. Here is an Ackermann function. This is like a very standard function that is used as an example for some recursive function. It computes something. Whatever it computes is not important. The important bit is the Ackermann function takes two natural numbers, m and n, and it returns a natural number. And ignore this for now, right? And what the function actually does is, if m is 0, then it returns n plus 1, right? That's one base case. If n is 0, right? Oh, that's the base case. If n is 0, then you call Ackermann, the recursive call on Ackermann, where the first term decreases, right? And if or else Ackermann function, if m is neither m is 0 or n is 0, then you call Ackermann with m minus 1, Ackermann of m, n minus 1. The important bit here is that at every recursive call, F star has to have this, uh, has the obligation that it can prove termination, right? So the way it typically goes ahead and proves termination is that it looks at the order of the arguments and sees whether the arguments are decreasing. Okay, so I have a recursive call here, the first recursive call here. So the input is mn, and the recursive call is on m minus 1, and m is a natural number. So m minus 1 is less than m, and m is a natural number, so this rule applies. So I know that this particular function recursive call terminates because eventually it has to go to 0, right? So let's look at the other one. Let's look at the outer one first. Again, the same rule applies, right? So Ackermann is here, and then m minus 1. Of course, this is smaller than m because of the less than relationship for natural numbers. That's fine. But if you look at the second argument, this is another recursive call to Ackermann. Here m does not decrease, right? The input is m, and this recursive call is also on m. So what f star does by default is that if the first argument does not decrease, it goes ahead and checks whether the second argument decreases. Actually, the second argument can be related by this well-founded ordering on expressions. So the second argument is now n minus 1, which is smaller than n, so that goes through. Okay, so essentially there is this notion of decreasing. There is a notion of well-founded ordering on the arguments, right? And that is what it is using. And you can make it explicit by this decreases metric. So you can add this annotation. You can sort of think about this as an extra annotation that you can add to functions in order to show f star that something is going to terminate. And the decreases metric here says that it's a lexicographic ordering, right? So it's the lex tuple here. Consider first that m will decrease. If m does not decrease, then n will decrease, right? That is all it is saying. Actually, it doesn't matter here. I'm just making it explicit. But by default, even if you don't give this particular definition, it goes through. But f star by default, the default metric that f star uses is the lexicographic ordering of all non-function arguments. So if you have a function, higher order function, then you cannot describe whether one higher order function is less than the other one according to well-founded ordering. But the default one is the metric that you see here. First, consider whether the first one decreases, the second one decreases. Otherwise, keep on moving to the other arguments. Okay. So let's see how this works out. So here is the Ackermann function, right? And this is the same as what I have here, just to show that this compiles. Okay. And this Ackermann 2 function is the same as the Ackermann function, except that I just removed this decreases metric here. I just want to show that by default, that is the metric that we use. Okay. Yeah. So here is a different function. this is also an Ackermann function. This is also computing the same thing. But what I've done is that I've reordered the arguments, right? So observe that I'm taking m first and n first. Here I'm doing n and m. So in the recursive calls also, I'm sort of reordering um, m and n, and similarly for all of the recursive calls, I've just swapped the arguments order. Essentially, this is computing the same thing except that the arguments are in different order. So here, um, the key point is that the decreases metric for Ackermann function is that m first decreases and then n decreases, right? So m decreases, here m decreases. If m doesn't decrease, n decreases, right? So here, if you sort of see this function, right, I have to explicitly add this annotation that first m decreases and then n decreases, even though the order of the arguments is in different order. So this actually type checks. But what happens if I comment this out? So unlike OCaml, you can also use double slash to comment, but that's a minor thing. But if you sort of comment this out, you will see that f star will complain, right? So it says that it couldn't prove the termination of the recursive call because um, because of the fact that it is expecting the first argument to decrease. It is a constant here. So it doesn't know, right? It can't reason about the control flow. I mean, it can't solve the halting problem. So essentially, it's looking at this one and says, okay, I can see that the first argument is not decreasing. So how do I know that this function is going to terminate? I don't know. So you have to prove termination for me. And yeah, so essentially the error is big. Oops, I don't want what happened. So the error is big, but essentially what it says is that could not prove termination of this recursive call, is what it is saying. You won't have to bother with this too much, but this is a thing that happens. This is a thing that happens behind the scenes, right? And really, for the decreases metric, you can give any total function. So if you say I have a list, right, and if you're writing some complicated program on a list, uh, if every recursive call will sort of say the length of the list is decreasing, you can add decreases metric length of list. And what it will do is it will compute the length of the list for the input, right, statically, because it has the SMT solver to do it. And then it says for every recursive call, does the length of the list actually smaller than the input list? If it is, then it will accept it. This can be very, very, very expressive. You can put any function, any total function here. Total, just as we define totality, right? Total functions are those which are known to be terminating and does not have side effects. Okay, so that's the challenge there. But I don't think we will come across those examples. So that's why I'm not showing it here. But that's the idea there for termination. Questions on this before moving on to the next topic? Okay, so yeah, okay, play around with this. But so I said total effect, right? So when I say there is something about totality, then you have to. I mean, the reason for introducing totality is that there are of course other effects that you want to describe. And one very useful effect that we want to describe is divergence, right? Right. Um, Divergence is just a technical term that we use to say that some particular code may loop forever, right? So this is the factorial function that we had earlier, right? So um, so this particular annotation cannot be the type annotation for this function. Why? Because this function, if you give -1, will not terminate, right? And totality requires termination. But it is, of course, sometimes useful to write functions that do not terminate. A good example is something like a web server, right? In the real world, you have a web server which always keeps running. You get a request, it responds, it keeps on looping, right? And it keeps on doing useful stuff. And it is not like after 10 requests it will terminate or after 100 requests it will terminate. I just want to say until I actually terminate this program by externally, I just want to keep doing this. In order to even express that logically, you want this notion of a divergence. And that is what we have here. So you could annotate the factorial function that takes an input and returns an input with the divergence effect. When you call divergence effect, um, you use this dv as the indication for the effect, right? When I say int arrow dv int, I'm saying that this function takes an integer, returns an integer, and has divergence. So it may possibly not terminate. Doesn't mean that it always runs forever. If you give, if there are some inputs for which it might not terminate, right? So a web server is one example, right? But you can also think about more familiar examples that we've seen earlier, where divergence is a useful property. Uh, One of those is an evaluator for an untyped lambda calculus expression. So recall that untyped lambda calculus can express infinite programs, right? Because we can describe the um, y combinator and z combinator. We also have self-application. So if you write an interpreter for simply typed lambda calculus, it will not terminate, right? That particular interpreter cannot be shown to terminate for all lambda calculus programs. So here is a very simple evaluator, takes an expression, returns an expression. So the idea is that the input expression is a lambda expression. The output expression is also a lambda expression, and it has divergence because untyped lambda calculus has divergence, right? And the idea here is that you pattern match with E, we are describing full beta reduction, right? So reduce everywhere, actually normal order, but that doesn't matter. We reduce everywhere that is possible. So if you have an application where the left hand side is a lambda and the right hand side is some expression, right? You go ahead and do the substitution, right? So you substitute for x in E1 the expression E2, right? The order of the arguments doesn't matter here, and then you recursively call eval. If you have an application, right? So of course we are using pattern matching here. So if this rule doesn't apply, then E1 is not a lambda. It is more complicated term. We have to reduce it. So if it is an application where E1, E2, you go ahead and evaluate, recursively call the same thing, where you evaluate E1, right? You evaluate E1, that's going to reduce to some expression, and you recursively call eval on that. If it is a lambda x E1, I also want to reduce within the body of the lambda, right? So that's something that call by value and call by name doesn't do, but normal order and full beta reduction does. So all I'm saying is, if you just have a lambda, the given expression is just a lambda, and if you are able to reduce within the body of a lambda, just go ahead and reduce it. So go ahead and call evaluation within the body of the lambda. If none of these rules apply, then you're done essentially, right? So you take an E and then you return the same E. So of course, this untyped lambda calculus can loop forever. So here is um, so before I actually go on here, let's look at the code. So just to make sure how we encode this one. Um, yeah, so this factorial function will be accepted because I have I say it's an integer to integer function, but with divergence effect. So because I've explicitly said it can diverge, this is accepted. So the way I express the AST for the lambda expression is that I have an application which takes an expression, another expression, and itself is an expression. A lambda, the variables are indicated by natural numbers. This is like a very standard thing to do. Um, um, yeah, so I think I'm not going to expand too much on this, but instead of using variable names, we just use natural numbers in order to indicate variables here. So I'm saying that a lambda is described by some variable, and variables are indicated by natural numbers, and the body of the lambda is expression. And when you construct a lambda, you just get an expression back, and variables are themselves just natural numbers, and variables are also expressions, right? So substitution is very standard, right? I'm doing substitution here, but I'm not capturing. I'm actually implementing a naive substitution. So recall that when we had to properly do substitution, we had to do capture avoiding, right? We had to sort of prevent two cases where a constant function does not get converted to a um, um, uh, identity function, and then identity function does not get converted to a constant function, right? So this is capture avoiding. So I'm not doing any of that. I'm just implementing a very simple substitution just to get the point across. And then evaluation itself, right? So is just what we saw in the earlier slide. This is the same as what we have here. So that's the evaluation. That goes through. The only reason that it goes through is that it's a divergent effect. If it's not, we cannot prove that this particular function will terminate because it won't, right? A good example is this. So this is the omega operator, right? This is self-application. So I have lambda xx applied to lambda xx. You can apply this lambda for substitute this term for this x, and what you get is the same term again, right? Oh, okay. So this should be lambda x applied to x, and x applied to x, right? So what you get is the same expression again, and you can keep reducing this forever. This is just the infinite loop. Um, and instead of x, I'm using 0 here, right? That's the only difference here. So lambda x, apply x to x, lambda x, apply x to x. Those are the two terms. And I'm actually applying this first term to the second term. And that's the application here. This one type checks, right? I'm actually not running this because if you run it, it will go into an infinite loop. But the point that I'm making is that if you ever wanted to express, I mean, it's very common, right? We wrote OCaml programs where we said, "Oh, here is the interpreter for untyped lambda calculus," and we did all the sort of fancy encodings, and we were able to show certain things happen. Um, Even though that was an academic exercise, I wouldn't call it like we were doing something very fancy, very realistic, very pragmatic. But the fact that we were able to do it just as a recursive function is something enabled by the fact that OCaml allows infinite looping programs, right? This particular definition of recursion is not something that you can write in Coq. You have to adopt some other way. There is a way to do this, but it is not through functions. It will be very, very explicit, and we will go through it step by step. You have to explicitly define that as a data type, and we will see why that is the case. And much of the further courses about proving programs is about um, how to handle languages which have interesting effects. So divergence is an effect, right? But Coq itself is a Spartan language. It only allows total functions. So how can you prove properties of interesting functions? Things like non effects like non-determinism, divergence, maybe throw exceptions and so on. How do you describe that in a smaller settings and prove properties about it is going to be the further study. But for now, the point I want you to take across is that F star being a pragmatic language for writing real effectful programs, you can write this function as a recursive function, right? That's the only point that I want you to take away. We will come back to all the other things later, right? And the other point is that you cannot write this function in Coq. If you were to do the exact same thing in Coq, Coq would complain that I cannot prove the termination of this function because termination cannot be proved. Um, that's the idea here. So any questions on this so far? So this is sort of the point I want to make is that F star is targeted at a more pragmatic audience, right? Their idea is to sort of combine the power of SMT solvers along with a practical language like OCaml, so that they can write real programs. That's where this is coming from. Okay, so if If there are no questions, I mean, of course, you can ask questions. Stop me anytime if you have questions, right? You can also ask questions later. In other classes about previous classes, I'll try to remember and try to answer questions. But for now, let's keep moving forward. So yeah, okay. So we've seen two effects, right? We've seen this total effect, which basically means, oh, no side effects. And then it actually terminates. And then we saw divergence, which simply says that the program can loop forever. But there are some other interesting effects that you can actually describe. Um, there are effects in F star known as ST, and ST effect is any computation that may diverge, read or write or allocate new references on the heap, right? So we do not have the notion of references, right? Mutable references in Coq, and we do have references in Coq, references in F star, which we will come back to in a later lecture. But those can be reconciled by um, tagging those functions as ST functions. ST sort of stands for state. It's a stateful function. It is actually manipulating state, and you can read and write allocate references on the heap. And what it converts to is actually references in OCaml, right? So it can be very, very efficient. So you can write efficient programs, but also prove properties on it, right? And then there is an exception effect, and the idea is that such a computation may diverge, it can run forever, or raise an exception. Exception is just ML exceptions, right? And then we actually have an effect called ML, and ML just stands for anything that you can do in OCaml, right? And the idea is that such a computation in OCaml programs can diverge. We can allocate references and arrays. We can read and write references. We can allocate new locations, right? Fresh references. We can also raise exceptions. So if all of these are allowed, we just tag them as ML effect. Just to say that things that we are writing are not total functions that we are using to prove. We're actually writing effectful code. So ML is a effect that you annotate those sort of functions, right? We'll see examples later. So so we saw this nice idea of subtyping, right? That a nat is a subtype of an integer. And similarly, if you sort of think about the effects here, ML encompasses all of the effects that are in both ST and exception. And similarly, ST, right, is sort of like a bigger set than, say, total. So you have this nice property of what is known as sub-affecting between these computations. What does sub-affecting mean? So sub-affecting essentially means um, the same idea as subtyping, but used at the effect level. You can use some function that has a particular effect, right? Some function, say, that has a total effect in a place where it expects a divergent effect. That's fine, right? So the context that is expecting a particular function is expecting a divergence effect. So give me a computation that can perform divergence, I will do something on it, right? At those places, you can always pass a total function because the total function does not diverge, and it satisfies all the properties of a divergent function. Similarly, any function that has an ML effect. So if your program has a higher order function argument, which is saying I will accept anything that has an ML effect, you can always pass a total effect there. The idea is that any total function also satisfies anything that is expected for ML, right? And this is known as sub-affecting. And this is important. Why is this important? It is important for uh, just the ease of use. So here is a simple function, right? Here is a simple function uh, that I'm defining Baz, right? I'm defining a Baz function that does something very silly. It calls factorial 3, this divergent factorial, on -1. Of course, this is going to loop forever. But for whatever reason, I just want to write this function where I say increment 2 plus factorial 3 of -1. See, observe that increment function itself is a total function, right? I'm using total function, and I'm using the result of a total function and adding that with the result of a function that diverges. So you have to sort of reconcile these two, right? So you have to, of course, I'm using addition. So I'm sort of also using subtyping here. So increment function expects a natural number, returns a natural number, but I can always consider that to be an integer. I can consider that I'm adding two integers here, but I'm also, the whole thing also, I can consider to be a divergent function, right? Because this is divergent, but this is total. I can consider all of it to be just divergent, right? So the fact that I can easily combine this without type annotation, coercions, explicitly saying that consider this function to be a divergent function, all of that is happens automatically under the hood thanks to sub-affecting that we have going on within F star, right? This sits underneath and does the hard work for us. Okay, so yeah, so here is a code example. So you cannot have pure code called divergent code, right? So here is an example. So factorial 3, if you look at the type annotation, it says it's a divergent function, right? Um, and I am calling the foo function as a total function. This is not possible because a total function cannot contain a divergent function as a cannot call a divergent code at all. So this particular function will not type check. So if you try to type check this, so it says that computed effect div, right? But I really expected a total, right? So that is what it is complaining because I have this annotation here, explicit annotation here. So this won't go through. So what this prevents is that we only allow reasonable effects to mix. So if you expect a total function, you statically prevent all of the divergent functions from being called, and only pure functions can appear in specs, right? Because we are doing static reasoning, right? If you want to reason statically, of course, go back to what we said about infinite loops. If you have infinite loops in your logic, if you have divergence in your logic, then you can prove false, right? So we saw this example in talk. So anything that can appear in the specifications, in the refinements, in the curly brackets, has to be a total function. So here is a type that I'm defining, right? A silly type, a type tau, which I say is an integer, but I say the x is equal to factorial 3 of 5. Again, factorial 3 is a divergent function. Even though 5, if I call 5 on this factorial, it will terminate, right? But the type annotation says that this function is going to diverge. And F star always works with the type annotation, not the actual values. So the very fact that this function is a divergent function will not allow this type definition to go through because, um, yeah, I mean, F star is not the best of languages that produces nice type errors. But the problem here is that it is complaining that this particular type, which it can, which can appear within the curly braces, has to be total, right? The effect of anything that appears there has to be total. It has to be terminating. But factorial 3 is a divergent function. It cannot terminate. So that's why this is not allowed, right? So you cannot have divergent functions within specifications. Then you can, then the whole logic falls down, right? Because you can derive false, and if you can derive false, then nothing is useful. Of course, divergent code can call pure code. So this is the example that we saw in the slide here. So divergent code can call total functions. So divergent function can call a total function. So that goes through, right? So sub-affecting is in play here because this is a total effect, and we are sort of lifting it to a divergent effect. That is allowed because sub-affecting, there is sub-affecting between divergence and total. So F star is a very rich language. You can define your own effects as well. I don't know whether we will get to that point because that sort of um, and it's useful to do that, but it might not be useful to get the overall idea of what we mean by programming languages for this one. So I'm not going to dive too deeply into this. These are not baked in, right? The point I want to get across is that you can define your own effects. and we won't delve too deeply into all of this. Very again, just like Coq, right, where the core language of Coq was very, very, very small, and everything else was encoded using just the for all and inductive types. So there is a similar logic under play for these this language, and much of what you see here, you might see a lot and lots of syntax and annotations and things like that, but all of these are sort of compiling down to something very, very fundamental. That's the beauty of these languages, right? Because we are doing formal reasoning. If the core of the language is small, then any property that you want to write about this core language holds. Anything that you write on top is just an encoding which you can compile down. So that's the idea here. Okay, so let's I think we are going to, yeah. So it says switch to slides, but I don't have anything. So let's look at a real example, right? So this is directly taken from the F-Star tutorial. So I'm going to show you a simple example where we combine where we do static reasoning, but we also do dynamic reasoning. We write real world programs, right? So what we are going to show is a simple model of access control, right? I want to describe a program that um, has access control for files, but implemented using refinement types. So what I've included here is I first included the exception effect. I've also included all. All simply says it brings an ML as well, right? So I've just opened it. I'm not using it here. I just opened it. It is part of the compiler library, right? So it comes from this file that is described there. You can have a look at what all brings, but that's not important. I'm just opening it here. Okay. And then I define a type file name. This type is just an alias, right? So whenever you see a file name type, it basically stands for string, right? And I now write a function called can write. Can write is not a recursive function. It's just a function. So it takes a file name, f file name, and if f is exactly demo/temp file, it is going to return true. Otherwise, it is going to return false, right? So observe that I'm not even adding a type annotation here, and the type that is inferred for this one is a file name to a tot bool. So I'm returning bool, that is obvious, but it is also a total function. So it can appear as part of the specifications. It can appear as part of the refinements. Right? And similarly, I have a can read function. And how do I define this can read function? Any file that can be written can also be read, and I can also read a readme function, right? So I have the temp file which I can write to and read, but I have a readme file which I can only read. Okay, so that's also defined. Again, if you move your cursor over it, you get this annotation which says that this takes a file name and then returns a boolean and has total effect. So, and then here's the interesting bit, right? So I say that I define a read function that actually reads a file. And what I want to say is that only those files which I'm allowed to read can be read. Everything else are statically rejected, right? And how do I do that? So read function takes a file name, and what is so special about this file is that it must have the can read capability, right? And can read is precisely described here. And because it's just a total function, it can appear as part of the refinement, right? So anything that can be read is readable. And if you read it, I'm saying that you can just get a string as a result. And because I'm doing arbitrary effects, right? I'm actually going ahead and reading from the file system. I'm tagging this as ML, right? And I'm not actually going to read it here. I just want to get the point across. So all I'm doing is that I'm just going to print the string fstar.io.print string, which actually prints to the console that it is a dummy read of a file f, right? And then just returns you that f string. This is just for illustration. So the point here is that only files that have read permissions can be read. Okay, so that's the read specification here, right? And it's quite nice specification, right? It says that read is a function that takes a file name and it has a can read. The file must have a can read capability. It must have the read permission. If you get the read permission, if the file has the read permission, then it is going to do some effect and it is going to return the content of the file, right? So that's what you should look at this as. And similarly for the write, so you take a file, you must have the write permission, right? um, on that file. You take a string, which is what you want to write, and when you write, you don't get anything back, right? Typically, we just say the write has succeeded, but write is going to might potentially have arbitrary effects because it is writing to the disk. I make it as an ML effect here, but the actual value that it returns is a unit value. And again, I'm not actually going to do the write. I'm just going to illustrate this happening. So I'm printing a string where I say dummy rate of string s to the file f, and all I'm doing is that that's all I'm doing. So again, the specification is the important bit. The specification says that take a file name, it must have the right permission, take a string, and it is going to do some effect, and the effect is an ML effect. So here is an example, right? So I have three files: a password file, a demo readme file, a temp file, right? Password, readme, and temp. So you can statically check whether this is true, right? Here is a function that does static checking. So there's I'm doing a bunch of reads and writes here. So I can read the temporary file. I can read the README file because why can I read the temp file? I can read the temp file because that's part of the specification, right? Um, temp file can also be written. So anything that can be written can also be read. README file can also be read, right? Those are the only two files that can be read. So I can read the temp file, I can read the README file, but I cannot read the password file, right? So that's why this is commented out. Again, I can write to the temp file. I cannot write to the password file, right? So this function type checks, right? But if you sort of remove these comments, these permissions are not true, right? So these permissions don't hold. Um, yeah. So actually, I should remove this one. So yeah. So subtyping failed. I expected a file with the read permission, but I just got a file name. So this password did not have the read permission, so that is why this is failing. So that's the static checking, right? So you can, I mean, even though this is a very simple example, you can sort of imagine this to be, you can encode rich policies about what is allowed. Um, and this underlies a lot of what is known as um, information flow control and so on. So there is a wide field about security where you have practices for capabilities. So certain files have certain capabilities. Um, you don't want the high assurance capability to flow to a low assurance place in your program. And if this is statically enforced, you know that that program does not have that particular class of bugs. And this is just an illustration of that, right? So static checking works through, but you can also do it dynamically, just like how we would have done this in ML, right? So I declare an exception called invalid read. I declare an exception called invalid write. This check the read. All it does is that it takes a file name and then it's going to do a read. But observe that there are no contracts here. There is no specification associated with this file name. And all I'm doing, as I would have done in, say, Python or Java or ML, is that I get this file name. I dynamically check whether I can read this file. If I can read this file, I read the file and I return the result. Otherwise, I just raise the exception, invalid read. Right? And similarly for write, if I can write to this file, I go ahead and write it. If I cannot write to this file, I just raise an invalid write. Right? So this type checks, right? Again, here is a dynamic checking. Statically, all of this is okay, right? I'm doing a check write to a password file. I'm just writing junk password here. Um, Statically, f star says this function is fine, but when you actually run this function, you'll get an exception back because that is the semantics of what we are doing here. And the difference between this dynamic checking and the static checking is the fact that static checking is statically capturing all the errors, but dynamic checking throws a exception. So yeah, anyway, so that's what I wanted to get across. This last line is not important. So dynamic checking is it's like doing what we would have done in regular languages, right? Mainstream languages, which is dynamically check what is allowed. And here we are actually encoding static policies. We are using the fstars type checker to do something useful. Even though this looks very simple, you can sort of imagine taking this example and then expanding it to add your own permissions and doing far more interesting things with the permission mechanism. Okay, so that concludes the introduction to fstar. So I'll stop here. Any questions on the material that we've seen so far? fstar is a fun language. I highly recommend you play with it. It's also not as um, yeah, I was going to use tedious, but tedious may be a good word to use. It is not as I found it not to be as tedious as Coq. Okay, so let's put it that way. It's actually good fun to program within fstar if you knew ML, right? So it's a good language to play around with, and there are lots of ideas that are floating around, which I think will land in other mainstream languages in the next decade. So you can be an early mover and play around with fstar. So what I will do is on Friday I will release an assignment that is based on the ideas that we've seen in this lecture, and we will continue from there. So if not, I'll stop here, and then we will meet again tomorrow. Thank you very much.